Our next talk is by Yunzhu Li, who is presenting 3D neural scene representations for visual motor control, and they'll be presenting remotely.
Thank you, and I will also play a pre-recorded video.
Hi everyone, today Yunzhu and I will present our oral work, 3D neural scene representations for visual motor control. This is a joint work with Vincent, Pocket, and Antonio. Humans have a strong intuitive understanding of the 3D world. When we see the same action from different viewpoints, we know they depict the same underlying content. We can also predict how the system would evolve for various materials. The predictive ability allows us to solve complicated manipulation tasks involving fluids and containers of different shapes. These abilities of humans are adaptable in a wide range of environments and go far beyond the reach of the current robots. In this work, we aim to build systems that can model the dynamics of complicated 3D things that might involve both rigid objects and fluids. We aim at learning the dynamics model purely from visual observations to support downstream visual motor control tasks. A key question to ask is how to learn 3D-aware representation of the environment from images. A good 3D-aware representation should accurately depict the underlying contents and allows us to perform control tasks from novel viewpoints. For example, given a goal image generated under a certain camera viewpoints, the robots need to achieve the same goal while its observed image are different from the goal image. In addition, we want the learned representation to generalize even if the goal viewpoint is outside the training distribution and study how well the robot can still accomplish the control task. There are many works investigating different forms of thing representations with different characteristics. One line of pre-work learns the dynamics model directly in the image pixel space. However, modeling dynamics in such a high-dimensional space is challenging, and these methods typically generate blurry images when performing the long horizon future predictions. Another line of work focuses on key points. Such models perform well in terms of category level generalization, but they are not sufficient to model objects with large variance, such as fluids and granular materials. Particles can model objects with high degrees of freedoms, but typically require strong supervision to map visual observations to particle states. Recent works like using the word model, Dream to Control learns dynamics in the latent space. However, the majority of these methods learns dynamics models using 2D convolutional neural network and the reconstruction loss. They have the same problem as predicting dynamics in the image space, that their learned representations lack equivalence to 3D transformations. Recent progress on neural radiance fields can reconstruct the realistic 2D images from the 3D scene representations by learning a simple feed-forward neural network. Such models take the prediction information of each 3D point x, y, z, and camera viewpoint theta phi as input, and output the RGB color and the density sigma for the 3D points in the scene. They compute the rendering loss by comparing the difference between the generated RGB result and the ground truth RGB values under a given camera viewpoint. In our setup, we apply randomly generated action sequences to the simulator and generate 1,000 trajectories as an offline dataset for each environment. Each trajectory contains 300 time steps. Each time step contains visual observations from 20 viewpoints. Here we show a video illustration of one trajectory and 8 images from viewpoints inside the training distribution. In this paper, we propose to learn time-invariant action condition dynamics model for visual motor control, the core of which is the ability to learn 3D-aware neural scene representations. Our model consists of 3 parts. In the left part, there is an encoder that maps the visual observations into a latent scene representation. Given an input image, we first pass it to an image encoder to generate the image feature. We then extract the features of images from the same time step by different camera viewpoints. To make the image features invariant to camera viewpoints, we use the time contrastive loss to pull features of images from the same time step to be closer. At the same time, we push the features of images from a different time step to be far away from the current image features. We then aggregate the image features from the same time step but different viewpoints using a state encoder to generate a state representation. In the middle part, we modify the nerve model to render the visual observation conditioned on the scene representation and the query viewpoint. The input is the position of each 3D point, the camera wave direction, and the state representation. The output is the color and density of that point. We use the same L2 loss used in the original nerve paper to reconstruct images. In the right part, there's a dynamics model that predicts the evolution of the latent representation conditioned on the input action. Given a state representation and an action, we predict the representation of the next state using a learned dynamic model. We compute the L2 loss between the predicted state representation and the ground truth state representation. The gradient from the loss is then backpropagated to the dynamics model to update its parameters. During testing, we first feed the input image at time t to the encoder to generate the scene representation st. The dynamics model then takes st and the corresponding action sequences as input to iteratively predict the future. Then the decoder synthesizes the visual observation conditioned on the predicted state representation and an input viewpoint. The overall system will allow us to synthesize images from novel viewpoints and predict the future states. Next, Yunzhu will show the experimental results and generalization to extrapolation viewpoints.
Hi, I'm Yunzhu, and here I'm showing the experimental results on action-conditioned future prediction and novel view synthesis. The left is a ground truth, and the right is our model's prediction over 200 time steps. The inputs to our model are the initial visual observations and the subsequent action sequence. The model predicts the future and renders the image from a query viewpoint. Our model makes reasonable predictions, but deviates from the ground truth when going too far into the future. Still, the model can be useful for planning and control when used in a closed loop. The learned model also works in cases where we shake a box of fluids together with an ice cube floating on the surface. Our prediction is a bit blurrier than the ground truth, and you can also observe discrepancies between the two videos. Still, our model captures the wave of the fluids and matches our intuition and can be useful in downstream tasks. Here's another example where 3 cubes fall down and collide with each other. Now, given the learned dynamics model, how well can it facilitate downstream control tasks, especially control from novel viewpoints? Here, the task is to match the fluid shape in 3D depicted in the goal image at the end of the control episode. Here's the control process, where the robot only takes a visual observation from one camera with a viewpoint vastly different from the goal. Here is the control result from the goal viewpoint. We extract the fluid particles from the underlying simulator and show the overlay between the resulting configuration and the goal. Our model matches the target configuration with a decent accuracy. Being able to control from novel viewpoints is great, but what about viewpoints that are outside the training distribution? It requires us to perform extrapolation generalization. Let us go back to the auto-encoding process and see what will happen when we encounter out-of-distribution images. The image will go through the encoder and give us an amortized estimation of the state, ST. When decoded directly from the amortized estimation, the results are not ideal and depict different 3D contents from the ground truth. To update ST and make it better at describing the underlying 3D contents, we employed auto-decoding test time optimization technique. Specifically, we compare the difference between the input image IT and the reconstructed image, and backpropagate the gradients of their differences with respect to the scene representation ST to iteratively update it. After the auto-decoding test time optimization, the resulting ST is much better at describing the underlying contents as evident from the decoded image. Here are some more results from our model that after auto-decoding test time optimization are abbreviated as AD. The rendered images are closer to the input images captured from out-of-distribution viewpoints. We compare our method with an alternative that uses a CNN decoder, and it produces much worse results. The key to our success is the use of neural implicit representations and the combination with a differentiable volumetric renderer. It injects the desired inductive bias that allows the model to be equivalent to 3D transformations. Given the updated scene representation for the goal image, we can use the learned dynamics model for model predictive control. Here is the control process. And here's the control results from the goal viewpoints and overlay between the results and the goal configuration in 3D shown in the fluid particle space. We compare our method with a 2D baseline trained using regular autoencoder and time contrastive loss. Our model is more precise at capturing the underlying 3D contents and generalizing to viewpoints outside the training distribution, where the 2D baseline shows a clear discrepancy with the target configuration. Here is another side-by-side comparison with the 2D baseline on shaking a box of fluids with a floating cube. Our model is more precise at locating the container's position when operating from a novel viewpoint. To show the necessity of modeling the fluid dynamics in our task, we include an additional baseline that uses PID control to reach the robot state in the target image without worrying about the fluids. Note that this baseline uses additional information, including the ground truth state of the robots in both the current and the target image. The goal here is to leave a small amount of fluids in the container at the end of the control episode. Naively matching the container's position and orientation using PID does not work. In contrast, our model first learns to pour a certain amount of fluid out and then tilts the container back to match the target configuration. We have also conducted experiments to validate our method on real-world data. We use 4D415 RGBD cameras to record a human subject pouring water from one cup to another. The cameras are calibrated and synchronized with a frequency of 15 Hz. To obtain the action, we attached an neighbor tag on the cup to obtain its 6-off pulse at each time step. Our model can learn from the data and make open-loop future predictions based on the learned representations. When compared with the ground truth, our model knows when the fluid pours out and fills the bottom container. And when the top container becomes empty. In summary, we propose to learn 3D array representations from visual observations that can perform long-term future prediction and novel view synthesis, and facilitate closed-loop feedback control from novel viewpoints that are even outside the training distribution. We hope this work can inspire future studies of more generalizable visual motor control systems for complicated dynamic environments. Thank you for listening. Yeah, happy to answer any questions.
Let's start with questions on virtual, if there are any. I guess it's pretty late there, so I'm not sure if there are. Any questions in the live audience? Jackie, you got a question?
My question is about the choice of environment. In many interesting manipulation settings, the objects of interest might be cluttered and occluded from view. So in viewpoint generalization, you'd want to be able to kind of predict object points on objects that are occluded in one viewpoint or occluded by the robot. Have you thought about these scenarios and how your model would generalize to these scenarios?
Yeah, thank you for your question. For this project, the original tasks we have been focused on were on fluid manipulation. And we have actually tried other representations like particles or key points, which doesn't work very well for our scenario. And what we end up finding is that this implicit representation as a regulator to learn this implicit dynamics model for visual motor control turns out to work the best. And applying this method in cluttered environment definitely, I think would be a good idea and can potentially deliver good results, especially in terms of estimating the accurate 3D locations of each one of these objects and encode every information inside this latent 3D representation. We haven't tried it for now, but I think our method can potentially generalize to those scenarios.
I think we had another question here.
Yep. Thanks for the nice talk. My question is, I have two questions. The first one is about the blurriness of the images that you are producing. And it seems like the objects are very blurry, but in the end, the tabletop is not. So I wonder why this is the case. I guess it's from the data set that you're trying to represent. And the second question is around what happens if you introduce yet another bucket of water that is increasing the dimensionality of the state you need to represent. Will this be captured, and how this will change the results you presented?
So the first question is about blurriness of the object, but not the table.
Yeah, in terms of blurriness, what we find is that if you see the original nerve work, they are overfitting to one static scene, and the results are pretty amazing. And we are taking a step to generalize that original nerve overfitting to a static scene to this dynamic environments. And this direct transition using this auto-encoding framework, what we find is that it can reconstruct objects that are relatively static, or if you see the robots that are articulated without any topological changes. For these objects, this extension can actually give you pretty sharp results. But for objects that have very large variation, like the fluid, or objects with topological change where the fluid can merge or split, it currently exhibits blurry results. We would imagine some other augmentations on neural radiance fields can potentially alleviate such kind of issue, like for example, pixel nerve that has better generalizations for more diversified set of things. But nevertheless, even if the fluid is blurrier than the ground truth, the predictive model is already becomes useful for us to do some visual motor control. If you think of our humans, when we imagine how the environment would change going into the futures, our mind cannot give us very sharp predictions of the environments. Our prediction may also in some blurry states where we can imagine the general trends, but cannot imagine every details and expect them to be correct. Our current model shows that even if it's a little bit blurry, it is still useful. And in the future, I think other techniques based on nerve to extend this kind of pipeline can potentially alleviate this issue.
Francesco's second question was about a second bucket of water. Sorry.
Yeah, I don't think our current our methods currently only train on each one of the environments. We have to train a separate model for it. And for this case, I don't think the trained model on one environment can generalize to environments that have more buckets of fluids than during training. So, and a natural extension to it would be to see how well this method can work in cases where you have some ideas of compositionality inside your representation. Now we condense everything into one single vectors, but that's won't give us a good ability in terms of capturing compositional system where you add objects or remove objects or split objects into multiple locations. So having a more structured latent space instead of one single vector can potentially give us a much better generalization in terms of multiple buckets of fluids than during training.
I actually have a follow-up question to Francesco's second question. So what is the largest system that you can have with nerve at which point it starts to break down? Or in other words, what doesn't work right now?
If you look at, actually this model is not perfect. This is our first trial for combining the neural radiance fields in the robotics, in our robotics pipelines. And if you look at the tasks where we pour in a fluid or shake a box of fluids, the movements of the container are actually pretty restricted. For example, if you're pouring, it's relatively move in this in one direction. If you shake a box of fluid, it's relatively moving just in a 2D plane. We have actually tried to apply this framework in an environment that has much larger variability, like granular materials, where you have a pile of granular materials, you can push it around, where you can depict a much larger set of possible variations in terms of the shape of the granular materials. And our method failed to capture that levels of variation.
Thanks. Any other questions on virtual? Okay, we're running short on time, so let's move on to the final talk for the oral session.